So at the very beginning, I'm going to talk about the structure of the test. So that's going to be the same as pretty much last night's review. And then since I posted the video and spent a great deal of time waiting for it to finish compiling, what I'm going to do is I'm going to talk about slightly different stuff tonight. So this afternoon. So I'll do a couple different examples. I didn't go over non-proof, so I want to do that just to kind of give you a heads up because that's that kind of stuff really wasn't covered. And stuff like that. Give you an example of one of those. And I did an example on the notes from last night, but I didn't actually do the example last night. So I actually want to do an example of those. And then I'll just open it up for questions. So what people had. So, and some people, do you need to be able to write, what do you need to be able to write for the special limit application? You need to actually write what the special limit is, give it a name, and then when you use it, equal sign, and then whatever you called it. So like in the packet, I called it special limit 1. And by the way, make sure on that problem set that you actually understand the U-sub. So I'll do one of those too. Just remind me. Okay, so what the test looks like. Let me pull this up from last semester. Spring. So there we go. So kind of if you are having trouble with the algebra, get that down first. Because that's kind of the, and if you want to talk to me about the algebra, you want to talk to the tutors, by all means, we'll do it. Stuff like, factoring, multiplying by the conjugate, stuff like that is the bulk of the important right, because if you can't do the algebra, it's going to mess you up. So make sure that you talk to me about the algebra. And then the last time I covered the idea. So are there any questions about that? I know that there's the one question about the sign limit. So I'll get to that in a moment. So last time I kind of talked about these kind of 4 types of proof problems. Okay, they were meeting the definition of. So I'm gonna move on to the proofs unless you have particular questions about how you do certain types of computational tricks. And I can certainly go through some of those with you. So I have these kind of 4 different types of proof of. So from last night, I talked about, what did I talk about? 4 different types of proof problems. And I'm going to put that in quotes here. Because they're kind of proofed-ish. So meet definition of continuity. Okay. Don't do this to me. Meet definition of derivative. Okay, so find a derivative using the definition. Limit of something drunk. And what was the other thing? exists a root or something similar. All right. So how do we feel about the idea that these are kind of the way, the types of proof problems that exist? 1 to 5. Okay, there we go. I have a lot of non-voters here. This is a test review, guys. Please vote. I don't know what you find difficult if you don't vote. Okay. All right. So, I want to address a situation that can happen, which is what's called a non-proof. And these are problems that look like the regular ones, but one of the things are not true. Okay, and this really happens with 2 cops, and it happens with IVT all the time. So let's say I took question 11 on the bootleg and modified it as follows. I say Daffy Duck says there's no function continuous on... Now, this is not question 11 from the bootleg. This is a modified version. So I made the modification so that you don't meet one of the conditions. So Daffy Duck says that there is no function continuous on -1, 2, so that f of -1 equals 3, f of 2 equals 0, but f of x never equals 2. Do you agree or disagree with Daffy? If you agree, prove Daffy is correct. If you disagree, explain Daffy's mistake and find a function that shows he is wrong. Okay? So what this is asking you for is either to prove it or to not. Now, what's the problem with Daffy's statement? I mean, it's going to be an IVT problem. You look at this, he's saying continuity on an interval, f of x doesn't equal something or equals something. This is a kind of IVT-ish problem. But what is the problem with Daffy's statement here? What does the IVT say? Has to be true. It doesn't say it has to be continuous everywhere, but it has to be continuous on the closed interval from A to V. Right? Not everywhere, but it has to be continuous on the closed. Okay? So if it's not continuous on the closed, you're going to have a problem. And notice here, there's no function continuous on -1, 2. Right? That's not the statement of the theorem. The IVT says what? Right? If f is continuous on AB with closed intervals and V is strictly between f of A and f of B, then there exists U N A B so that F of U equals V. Right? So you need this type of idea here. Right? You need that. You actually have to know the theorem in order to see, wait a minute, there's a flag on the play here, right? You can't do this. You need it to be done on the closed. So the solution to this problem is to say no. It looks like he's trying to use the IVT, but the IVT requires continuity on the closed interval. And then what you do is give an example. And even if it doesn't ask you for one, find one. And let me give you some tips on how to do that. But constant functions are your friends. Lines are your friends when you want to find examples of things. And piecewise things are good examples, right? This function right here is a piecewise function where f of -1 equals 3. F of 2, that should be a 2, equals 0. And it's 1 otherwise. And you don't even need the statement. All you actually need is the drawing. Okay? So this function is continuous on the open interval, but it's never 2. So Daffy is wrong. How do we feel about that, 1 to 5? And the opportunities for non-proofs will pretty much always to ask you to disagree or something like that. And they're not easy problems, right? Because they fit a pattern that you're used to, but they aren't that, right? They're asking you to think. So these tend to be the harder problems. So it depends. You can say that. If the thing doesn't ask you for a specific function, you can get away with just saying the explanation. However, it's usually better to actually give the explanation. It's usually better to give an explanation. I mean, to give a function that shows they're wrong. And you know, it doesn't always ask for that, but if it does, watch out for that. These can happen for 2. So, let's do an example of a 2-cop. So the general tips are this. If one of the conditions doesn't look right, stop and draw a picture. If you are missing a condition, stop and draw a picture. If you cannot seem to meet a condition, stop and draw a picture. Don't try to force them. Just draw a picture. So what is the big idea with dealing with these proofs? Give me a sentence that says what the big idea is. Summarize it for me. Yes, exactly. Draw a picture. If you're not quite sure what's going on, draw a little picture. Let's look at an example from last year's bootleg. Let's test 3. So let's see. Bootlegs. Quizzes. Bootleg. Here's a good one from last semester's bootleg. Am I actually still working, or is the thing looks frozen to me? Am I actually still moving? Okay, yes. All right. Sorry, I'm quite after last night. I'm quite distrustful of OBS now. Just like you're freezing a lot. I think it's Windows, not OBS's fault. I need to install Linux on this computer. Let's see. So let's look at an example. So here's the example from last semester's bootleg. Screen 2. It's right here. Yosemite-Sam says that this function here equals -1 by using two cops and a drunk, x squared minus 1 and negative x squared minus 1. Do you agree or disagree? If you agree, finish this proof. If you disagree, find and prove the actual limit and prove that the function does not have a limit. Okay. And the trick to this one, let me copy this into our notes here. Hold on. I want to go back to the tablet. Snip me. Let's see. Let's do this. So put it right here. So this is an example of a non-proof for two cops. Hello. There we go. Non-proof example, two cops. Okay, so there's a couple things in here, but what's the big deal about why is this wrong? Okay, well, what are the conditions on two cops? If what? If top of x is greater than or equal to f of x, greater than or equal to bot of x for x near a, and if, what's the other thing? The limit as x to a of top of x equals the limit as x goes to a of bot of x. All right, equals L. Then the limit as x goes to a of f of x equals L. So what is it I need to check here? I need to check that both of these conditions are true. Okay. Well, the first one looks like this, right? Is it true that so let's do this one real fast because this one's going to be the easy. Is it true that the limit as x goes to a of bot of x equals the limit as x goes to a of top of x? Well, what is a? Somebody give me an A. Are you able to hear me? Yeah, okay, so you are. What is A? Well, A is 0. So here, the limit as x goes to 0 of bot, I assume he wants that as bot, of negative x squared minus 1 equals 0 minus 1 equals -1. Okay. The limit as x goes to 0 of x squared minus 1 equals 0 minus 1 equals -1. So is this condition true? Yeah, so the second condition is met. Okay. Is everyone on board that I've met that condition? 1 to 5. All right, so let's try that first condition. Is it true that negative x squared minus 1 is less than or equal to f of x is less than or equal to x squared minus 1 near a equals 0, or near x equals 0? Is this true? Well, if we were going to set this up, how would we set this up? We would go, right, we'd go sine of pi over x minus 1, right, is less than or equal to 1. Negative 1 is greater than or equal to negative 1, is less than or equal to 1. And then we're going to multiply through by x squared minus 1. And notice near 0, x squared minus 1 is less than 0, so flip signs. And I'm just going to multiply through. And I wind up going through like this. So I'm going to multiply through by x squared minus 1. I'm going to wind up with the negative here is greater than or equal to x squared minus 1 sine pi over x minus 1 is greater than or equal to x squared minus 1. And this side here is what? Negative x squared plus 1. Wait a minute. What's wrong here? There's something wrong, right? This is not bought. So I go, wait a minute, this is not bought. Or top. Or bot. Does everyone see that? 1 to 5, how do we feel about that? That's not right. Something's wrong here. Correct? This is not the right function. When I multiplied through, I wound up with the wrong thing. So now I'm suspecting that this is wrong. Right? Because this does not equal one of those. All right? So let's go back to the original function and let's try something else. Let's sit down and go, wait a minute. The limit as x goes to 0 of x squared minus 1 sine pi over x minus 1. Okay. Well, this piece is going to go to negative 1. Well, what does this piece go to? If I plug in 0 right here, what does this equal? Yeah, it's going to be sine of negative pi. What is the sine of negative pi? Sine of negative pi equals 0. Is negative 1 times 0 a problem? Is that a bad number? The answer is no. That's a perfectly fine number. 0 is a perfectly good number. This limit is actually just 0. Okay? Now, note that this problem was on last year's bootleg, and it's not on this year's bootleg. It was a little bit too hard, right? But if I sit here and I go to Desmos and I actually look at the function, and again, we wouldn't give you a function like this. We might give you a problem like this, but we won't give you this type of function, because this type of function right here is actually pretty hard to just graph. I mean, you can, but what we probably wouldn't give you a function this complicated. Oops. So what is it I want here? I want x squared minus 1 sine of pi over x minus 1. Okay, and then I want my supposed things were negative x squared minus 1 and x squared minus 1. And if you graph this, you actually see what's going on here. This is in the wrong spot. Let me see. Look at this. The red is the drunk function, but here it's not drunk. And here it's outside. It's above what this guy was saying was top. Right? F of 0 is 0 here, whereas the two limits are negative 1. This thing's out of the bounds. One to 5, how do we feel about that? That, you know, again, this one's harder to draw than one we would give you. This one's really annoying. But you actually could do this little bit using your, you know, just sit there with your calculator and plug in a couple values near zero, and you'd see that it's outside the bounds. So 1 to 5, how do we feel about that? And again, this problem's harder than any one that I could actually give you on a test. So what's the point? Check to make sure your position, your things are correct before you just go off and do it. All right. I don't want to make you feel nervous. I'm just saying that you can see problems like these, where one of the conditions aren't met. What would be an example of like a problem where the other condition was the one you didn't meet? Right? I could have a situation where let's see. I could have a situation like this too, right? Right? Here I've met the between condition. Am I doing this right? So let me do this. Let me do this back here. So what am I looking at? Right. Okay. So let me just take a quick snapshot of this. And I want to put that here. This is what the picture would look like. Yeah. I could also have a situation that looked like this, where they were just, you know, not in the same thing. So this is another possibility here. So bot of x equaled negative x squared minus 1, top of x equaled x squared plus 1, but the limits as x goes to 0 are not the same. All right. So how do we feel about this possible situation? 1 to 5. How do we feel about this possible situation? I could have a situation where the limits just don't match of top and bot. So this is an example of a non-perf as well. Okay, so we're a little bit nervous. I'm getting that we're a little bit nervous about these non-proofs. So I wanted to, you know, just mention it, that they can exist. This is usually one problem, and remember, there's like 110 points. So if you're having problems with the computations, focus on that stuff, because that's worth a lot more points than something like this could be. Okay. All right, so there was the sign problem. Let's do one of those. So let's do this. Let's see. So let's do some of these sign problems, and then if you have special limit problems. So this is kind of like the one on the bootleg. Let C be a constant. And then find the limit as x goes to 2 of sine c x minus 2 over 2cx minus 4. Is that going to do it for me? No, because that's going to depend on C. Hold on. Let's just do this. X minus C over 2x minus 2C is the limit as x goes to C. All right, so how do we feel about what this question's asking us? What's moving with the limit? Does C move? No, C is fixed. Okay. So what I'm going to do here, so the limit, what I want to do is I want to find the limit of something with a constant in there, right? So let's say that C was 9. If C was 9, what would I do? Let's say you got the randomization C is 9. What would you do here? All right, that was your randomization on WebAssign. What would you do? All right, you do a U substitution and you get rid of the x minus 9. Okay? Now we've just got a C here. So this is a little more abstract. C doesn't move with this. So what I'm going to do is I'm going to make a U substitution. Well, the first thing I'm going to do is state the special limit. I mean, right away, this is a sign here, correct? What are you going to do? You're going to use sine of x over x, right? That's the only way to get at this. So what I'm going to do is I'm going to write that down first. I'm actually just going to write that down. I'm going to say right here, write this first. The limit as u goes to 0 of sine u over u equals 1. And I'm going to call that special limit 1. Okay, I'm just going to write it out. Is everyone on board with that? So I want to make this fit this. So what I'm going to do here is I'm going to say, and this is why this U substitution method is better. Instead of trying to make the thing match the pattern while leaving in everything, if you do the U substitution, there's a process that's mechanical now. Okay? All right, and that's what I want. I want a kind of mechanical process for making this happen. So what I'm going to do is I'm going to say let u equal x minus c. So this problem now becomes the limit as x goes to c of sine u over 2x minus 2c. All right, so now I need to figure out what I can do with this. Well, what can I do with the bottom here? Right, I can either factor the 2, and that's a perfectly good option. Right? So let's do that. Let's factor the 2. Okay. Out it comes. And then what have I got left? Now this is u. Let's substitute it. And by the constant multiple rule, that 2 can just come out. I've got one piece left here. That's that x goes to c. Well, I've got my special limit here. So wouldn't it be nice if u went to 0 and x went to c? Let's find out. So I know that the limit as x goes to c of u, in other words, u goes to 0 as x goes to c. So I'm going to replace this with that. And I still need my 1/2. I lost my baggage. Need to carry my baggage. And then I'm going to write SL1 1/2 times 1. And remember, I can only write SL1 because I said what SL1 was here. And now I've got an answer. How do we feel about that, 1 to 5? I mean, you can do it the other way, but it's harder to do it that way if you wind up with a minus and a plus. You can, right? So if I had, let's do another example. This was the other way to do it. If I had lim x goes to 1 of sine x minus 1 over x minus 1, right? It's rather obvious what's going to happen here. The only thing I have to change is this. So I go as x goes to 1, x minus 1 goes to 0. That's rather obvious. So I say this little bit here, and so what I have is, so I replace the limit, and then I have the limit as x minus 1 goes to 0 of sine x minus 1 over x minus 1. And then I can use my special limit. But I find that harder. Yeah, this is like number 8, I think it is, on the bootleg. Yeah. So here I've got 2 constants, but there's actually nothing really special here. It just looks bad. Okay? And that's another thing. Just as general advice on this test, there are problems that look bad that actually aren't. Right? So there exist problems So don't get like deer in the headlights on this stuff, okay? There exist problems that look hard but are actually just trying to intimidate you. And then a good example of one of those problems is number 8 on the bootleg, right? This looks hard because these things are, oh, I got a 2, I got a -2, I got a... But if you sit there and you just work it a couple of times, this one will actually work out. So you let u be the thing here and then deal with the bottom later. And actually on this one, the bottom, the Q just pops right off. The 1 over q you just pull out. You factor the bottom first and then get rid of it, and then it's kind of obvious what's supposed to happen. Well, not obvious, but you know, you get rid of that. So how do you feel about these now 1 for 5? So just, you know, there are problems that look hard. All right, does anyone have any more specific questions? Anybody? Questions? Yes. No, so you can't. So the question is, can I just factor out the 2 and then cancel the x minus 2's? And the answer is no, because the x minus 2 is trapped inside sine. So as a good example of that, ask yourself the following. Is sine let's say there was a 2 on the inside. So is it the case that sine 2x equals 2 times sine x? So I think I see what you're saying, but you can't just cancel things. You can't just pull that out. Yeah, I can't just cancel things out of there. Right? It's not the case that sine... Is it the case that sine of 2x over 2 is the same as... So I'll put a little equal sign. I'll put a little question mark. It's not the case that sine... this is the same as sine of x over 1, right? If I put pi over 4 in here, this side here is going to be 1 half. But this side here is going to be root 2 over, I'm sorry, root 2 over 2, or the square root of 1 half. Does that make sense? So, I'm sorry, try pi over 4, x equals pi over 4, right? So, sine of 2 times pi over 4 is the same as sine pi over 2. Right? So this is sine pi over 2. So sine pi over 2 is 1. That becomes sine of 1 half. Okay? Are you on board with that? But sine of pi over 4 over 1 equals the square root of 1 half. And they're not equal. Right? So these things are not equal. Okay? But it's a good question. It's an easy mistake to make because the symbols, right? This looks like multiplication, right? So it's an easy, and you even said the word of. And, you know, in middle school, you would, every time you hear the word of, you multiply, right? 1/2 of 1/4 is 1/8. You multiply them. Right? And that's bad now because you've heard the word of and you think multiply. This symbol, this little parentheses looks like multiply and it's not. So yeah, that's a failure in the way that mathematics has notation. That's a failure of mathematical notation. It actually confuses. All right, number 6E on the bootleg. Okay, so how do you feel about D here? What is this limit? This limit is just 100e to the pi, correct? This is a straight line, right? It's a limit of a constant. It's 100e to the pi. Okay. And then, so e to g. Okay, so what does this function 1 over x to the n look like? What does 1 over x look like? This should be a function. This is a very good question. So these functions, this is a function that should be absolutely buried into your soul. Let me do another Desmos instance. Because it doesn't, the function is, there's only 2 versions of this function. And this is that function 1 over x and things like it. So the details change. But the function is really the kind of shape, the thing that happens at infinity is exactly the same, and 0. So let's do this. So if I take the function 1 over x, what does that look like? It looks like that. So if you don't know this function, if someone says 1 over x and you don't immediately see this picture in your brain, I want you to print out this picture and stick it above your bed, right? Right there on the ceiling, okay? I want you to be looking at it every time you go to sleep. All right? I want you to see that thing. If you're a stomach sleeper, I want you to go get it stitched onto a pillow, okay? This should be the thing that you should dream about this function. When someone says 1 over x, this should be the picture that pops in your mind. How do we feel about that 1 over 5? How important this function is? Okay. So this, again, this function should be giving you nightmares. All right. Not, nightmares as in you're scared of it. Nightmares as in it shows up when, you're having a good dream. And suddenly you've got 1 over x showing up in your mind. Okay, this thing should be buried and embedded in your brain. Okay, so now what happens if I cube 1 over x? So if I take this function and cube it, what's going to happen? I mean, something will, right? But not really. Right? The limits as you go to infinity and 0 are still exactly the same. Look at this. I went from, this to that. It's something happened, but not a whole lot. Right? And that's true if I go to any odd number. There's 1 over x to the 17th, right? It takes a little longer to get to infinity as you head to 0, but it gets there. How do we feel about that 1 to 5? That if I have an odd power on the bottom, the end behavior doesn't change. right? It's gonna, whatever the odd power is, I mean, it'll make it, if I do 100, if I do 1 over 107, right? As it gets to 1, it starts hitting off to negative infinity really fast. And it takes a long time to get to 0, but it does eventually, right? I mean, it's just faster to get to negative infinity than in one sense. Right, and then it plops down right here. But it's the same basic function. Now, what's going to happen if I square it? Like instead. There's only one thing that happens. The left side flips to the top. Just as if I had taken the absolute value. That is the only thing that changes, right? If I do the absolute value, if I do 1 over ABS of x, right? I get the, right, 1 over the absolute value. So it's always positive. I get pretty much the exact same thing that happens if I square it, or if I go to the 4th, or if I go to the 6th. The only thing that happens is that the negative becomes a positive. And they're all the same. So how do we feel about that 1 to 5? Yeah, and if ABS wasn't over 1, you're asking an excellent question about the kink. That is absolutely true. I mean, right, so there's the classic kink function, and I can move it around if I want to by just doing something like this, right? There's ABS of x minus 4. There's ABS of x minus 6. All I'm doing is moving where the kink is. Oh, there's a limit at the kink. So that's a good question. Someone has a question about the limit. Yes, the limit here exists. This is actually a continuous function. So the limit as I go to 6 exists. But there's no derivative at the kink. Because the derivative is going to be -1 here to the left and +1 to the right, and there's no tangent line. So there's a limit, but there's no limit to the difference function. So there's no limit to the secant slopes. There's no, right? The regular limit exists, the derivative does not. That's a kink. Yes. The limit would be 0 at 6, right? At x equals 6, the limit is 0. The y value is 0, but the derivative is d and e. Awesome. Are there any other questions? Anyone have problems that they want worked? No, so the test, you don't get the test questions in advance. And the test sheet is not yet in Canvas. The answer sheet that you need to write your answers on. Will I be posting this? Hopefully I will be. It depends on the amount of time that I have this afternoon. But hopefully, yes, I intend to post an edited version of this video. But it depends on time because I've got a meeting at 2 and I've got a class at 3:30. And then and then we've got our class at 7. how does the evaluation of just x approaches something different from x approaches something from the left and from the right? So there's this question. I think what you're asking is about this situation here. So let me switch my graph here. So I think you're asking about something like this. I think you're asking about a situation where I've got something like, let's see, this goes here, and then I've got a hole, and then I've got like a point, and then I've got like a hole, and then I've got, we'll just do parallel lines here, something like this. So is this what you're asking about, where I've got a situation where the graph kind of looks like this? Is that kind of what you're asking about? Yeah. So, the question is, okay, so here from the left, as I approach, let's say this is 1. Okay. So here, the limit, and let's call this f. Here, the limit, as I go to 1 in the x space, the limit as x approaches 1 from the left. Okay. This says as x goes to 1 from the left. Right? That's what that 1 minus means. As I go to 1 from the left, right, of f of x, this actually equals like negative 2. The limit as x goes to 1 from the right of f of x, this is from the right, equals positive 2, or 1.5. While f of 1 equals like 0.2. Does that make sense? Okay. For number 12, let's see. Yeah, for number 12, you actually have to prove it. And I'll be going over this. So the question, there's a question also, what will I be going over in the 7 p.m. class? I'm going to be going over the proofs of the first limit laws. So I'm going to be going over the constant, I'm going to be showing how you prove the power rule. And then I'm going to be showing how you do the constant multiple rule and the sum law. This is actually in your notes. But just as a little preview, okay? The 7 p.m. class is the 7 p.m. Lecture. So you can watch it live or you can watch it on YouTube. Yes, Mondays and Thursdays. So question 12 was, let f and g be differentiable functions. Then prove d over dx of f plus g of x equals f prime of x plus g prime of x. Okay? So what is, just out of curiosity, question. What is f plus g of x? What does that mean? Well, f plus g of x is defined as f of x plus g of x. Okay? Yeah, but remember it's two sets. F plus g equals the set x, f plus g, f of x, comma, f of x plus g of x for x in their common domain. Okay, so remember that this function itself is not just it's two functions added together, actually means a set of ordered pairs. Okay, so what I have to show is that the change in, as I move to the right, the change in the y-coordinate is the same as the change in the y-coordinate for this, plus the change in the y-coordinate for that. So the question's not quite as easy. I mean, it's not really hard, but it's not quite as easy as it looks. So you have to say something like this. Let I want to say H, but then I'm going to use H in the definition. So I hate that it's H. It should not be H. It should be W on the bottom, but okay. I'll call it Q. Let Q of X equal F of X, F plus G of X. I should use S, right? Let's S of X equal F plus G of X. Okay. So now S prime of X equals the limit as H goes to 0 of S of X plus H minus S of X all over H. Okay, so how do we feel about that 1 to 5? And I have a 2 p.m. meeting, so I have to go pretty soon. How do we feel about that? And again, this is a hard question. It's much harder than anything I could ask on test 1. Now, test 2, it's fair game. Definitely. And it's what I'm going to be kind of going over tonight. So now what I'm going to do is I'm going to take this S. And I'm going to say, okay, well, what is S of X plus H? But the definition of S, and this you have to be careful here because this is not multiplication. By the definition of S, it's this. And here's the part that's going to be brutal, is you have to keep that X plus H together. So S prime of X equals the limit as H goes to 0 of S of X plus H minus S of X all over H, which equals the limit as H goes to 0. Now here's what's hard. F of X plus H plus G of X plus H minus F of X plus G of X all over H. That's the hard part, is making that jump. D, that's the verb. So that's a verb. So d over dx is a verb. It says take the derivative of what follows. It's a command. Do this now. All right. And then, so what I'm going to wind up with here, if I do this right here, I'm going to wind up with, what I want are two limits here. So what I want at the end is, let me write that here. What I want is the limit as H goes to 0 of F of X plus H minus F of X all over H plus the limit as h goes to 0 of g of x plus h minus g of x all over h. Okay, so what I'm going to do here is I'm going to break this up with the sum law. So the first thing I'm going to do is I'm going to expand that because that's just annoying. So now what I'm going to do is I'm going to move this over here and this here. So I'm going to take my little pen. The D, I'm looking at this question you have. The D is not a symbol on its own. The symbol is D over dx. So what I'm going to do is I'm going to take this little piece here with this plus. I'm going to kind of move it over. I need the plus. And what I'm going to do is I'm going to move this F right here. And I'm going to take this G of X plus H, and I'm going to move it right here. So that's just a little bit of algebra. And then what I'm going to do is another piece of algebra. I'm just going to break everything up. So it's going to be F of X plus H minus F of X over H. And this is all together under the limit sign. And now what I'm going to do is I'm going to do this. I'm going to attach the sum law. So by the sum law, since both of these derivatives exist, f of x plus h minus f of x all over h plus the limit as h goes to 0 of g of x plus h minus g of x all over h. And this right here is the definition of f prime of x. And this right here is the definition of g prime of x. So this whole thing equals f prime of x plus g prime of x q e d. So the point here is what I want is I want the definitions of this and this. How do we feel about that 1 to 5? That is a hard problem if you've never seen it work before. So the idea is that what I'm after is the definition of what I'm after. That's hard because you have to combine this thing into a new function here. And then you kind of have to, be meticulous about what's going on. So it's not an easy problem. And if you want more of this, tune in tonight at 7. I'm going to do the proof of the derivative of the power rule. I'll probably do the constant multiple rule as well. And I might even do the constant rule, although that one I like to assign as a problem to work out for yourself. Are there any other questions? Okay, I have a meeting that I have to go to. I will be on Discord. You can send me messages. I'm going to be free-ish around 5 p.m. today if you want to ask me questions. Oops. Sorry. I was telling you something in the stream post. I've got a meeting to go to. If you have more questions, I'm going to be around 5 p.m.-ish. I will be happy to answer questions, but I won't be in the office chat thing. You'll have to send me a direct message. But that'll be around 5 p.m. today, which is before the 7 p.m. class. I'll be happy to answer questions. And remember, I have extended office hours tomorrow, but they're not at the standard time, and they are not on campus. They're only virtual because Discrete has a test. Are there any other questions? And there were questions about getting this posted. I will. I'll try. Let me put it that way, because I'm not sure if I'll have enough time. Because the rendering takes the things. Okay, so the office hours tomorrow, I posted that on I posted that on Canvas in an announcement. Which for some reason it won't. Oh, because I'm clicking on the wrong thing. So I posted that on the announcements. There will be special 2 p.m. to 5 p.m. open office hours on Discord tomorrow. And that's after the discrete test, and the discrete guys don't have homework for the weekend. So it should be mostly calculus people. At 5 p.m., I'll be answering a lot of discrete questions. But these are pretty much exclusively you, because the discrete people are going to be like, we're done. Any other questions? Okay, I got to go to this meeting. I will talk to everybody later, okay? So I need to stop doing this.